Hi everyone, today we'll start the second topic, which is derivatives. Alright, so I'm sure most of you have learned differentiation in your high school advanced math or additional mathematics. Right, so what we will do in this topic is actually slightly more advanced than what you learn in high school. It's actually more conceptual and more technique, and of course we will learn the derivatives of those transcendental functions as well. Right, so we'll start with, by the way, today I will not use those differentiation rules like chain rule, product rule, quotient rule, and what else, sum and difference rule. That one I will leave it to the next lesson. So today I'm just going to give you an introduction to the concept of differentiation. Why do we need to find the derivatives, and also the first principle. Alright, so whenever we talk about first principle of derivatives, we always start with the tangent line problem. Okay, so we need to understand what is tangent line. I'm sure you have seen this word in your coordinate geometry or college algebra. So just a very simple definition for tangent line. It's actually a straight line that touches a curve at one point. Okay, that touch at one point. So in other words, it only intersect with the graph of function, or it not necessarily is a function. It can just be a curve touch at one point, intersect at one point. So in the diagram here, the one in red is the tangent line. Alright, this red color line is the tangent line to the curve, to the blue curve. So as you can see, they intersect at point P. So what is wrong with this tangent line? Why do I have a problem with this tangent line? Okay, so our problem is we want to find the equation of tangent line, and I will explain to you later why do we need this equation. But as you learn in your coordinate geometry or college algebra, how do you find the equation of a straight line? You use a formula which is y2 minus y1 equals to m times x2 minus x1, right? But there is a huge problem here. In order to use this formula, because we don't know the value of m, so we need to have at least two coordinates on the line. However, we only have one coordinate, which in this case is point P. We only have one coordinate. Then how do we find the equation of tangent line? Here's come to with another concept, another line that you see in this diagram, which is the one in black, and we call them secant line. Secant line. Secant line. Alright. So secant line is a graph that touches is a line that touches the graph on at least 2 points. So now, if we have the equation, if we have the coordinates of those 2 points that intersect with the curve, can we find the equation of this secant line? Yes, right? But what is the relationship between secant line and tangent line? Let me draw another secant line with green color. Alright? So if we have another secant line like this, which is slightly closer to our point P. Okay, now our point Q is here. Yeah, this is our Q prime maybe. And it is also a secant line as well, yeah? Secant line. Do you notice that the distance, the x coordinate of P and Q becomes smaller? In other words, the h becomes smaller, right? Now this is our h prime. So if we do it again, we make it closer to our point P again. Okay, let me draw one more for you. Somewhere here. So it is here. Okay, this is our Q, maybe double prime. And this is now, I'm not sure if you can see this. This is our H double prime. Okay, it's a bit messy here. But what I want you to see here is, as we decrease the value of h, which is the difference in x coordinate between the 2 points of secant line, the secant line will eventually becomes the tangent line. Am I right? So the key here is we want the distance between x0 and x0 plus h to be as small as possible. As small as possible. But we can't have 0. Why? Because if it is 0, then your equation will be undefined, right? You will have the slope will be something over 0. Let me write one more for you. From here, from this equation here, the slope is actually y2 minus y1 over x2 minus x1. So what happens if your h is 0? If your h is 0, means your x2 minus x1 is 0. Everything divided by 0 is undefined, so we can't have that. But we still want it to be as small as possible. What do? We take what we learned in the last topic, which is limits. We take the limit of, okay, the slope will be the limit of, what is this? H, right? H approach 0 of, who is our y2? This fellow here, right? F of x0 plus h. F of x0 plus h. Who is our y1? Is this fellow here, which is minus f of x0. Who is our x2? It is this fellow here, which is x0 plus h minus, who is our x1? Is just x0, right? So if you simplify, you see this x0 and x0 can cancel. It will just be the limit as h approach 0, f of x0 plus h minus f of x0 over h. And this is the slope of our tangent line. Okay, slope of tangent line. So now, when we want to find the equation of our tangent line, instead of finding two coordinates, we now have one coordinate plus with the slope. Then we can also find the equation of tangent line, isn't it? So this is what we always start with when we talk about the first principle. And this is actually called the derivatives at a point. Or maybe I should, okay, let me go to the new page. Then I'll explain to you what is this derivatives at a point. At a point, which is this fellow here. The limit as h approach 0, f of x0 plus h minus f of x0 over h. Okay, so this limit here, what does it mean? I already told you that it is the slope of tangent line to the curve at x equals to x0. This is what we had from the tangent line problem, right? It also means that the slope of the curve y equals to fx, for example, if this graph, the one in blue, if we call it y equals to fx, it is also the slope of y equals to fx at that point, at x equals to x0. Okay, and if you remember from your coordinate geometry or our college algebra, what is the meaning of slope? If you have a straight line, just a simple straight line, and you find the slope, this slope actually means it's actually the ratio of the change in y over the change in x, right? In other words, it is how much your y changes as your x changes. In other words, we call them rate of change. So if this limit here is the slope of the curve at that point, it also means that it is the rate of change of this fx with respect to x. Yeah, we have to be very careful with this. It is with respect to x, because later in the chapter you'll learn about parametric equation where you with respect to something else. Okay, also at that point, x equals to x0. Or you may call it in chemistry, I think when you study the rate of change, it is actually the instantaneous rate of change. Alright? Then last but not least, this is also the derivatives, like I told you, the derivatives at okay, maybe I shouldn't write like this. The derivative f prime x naught. And I will explain this later. I will explain what is this later. Okay. And actually it's on the next slide, alright? So because this is very useful. This is very useful. As you can see, we can find the slope, we can find the rate of change, and in economics it actually represent the margin or whatever. Okay, so it is very useful and very important. That is why like what's that? Like your trigonometric functions, because it is very widely used, you will frequently use it. So people invent the mathematician invent the trigonometric limits like sine, cos, tangent, because the ratio between the hypotenuse and your adjacent is commonly used, is frequently used, right? So similarly, the mathematician also came up with the idea to make this a function. So now we are seeing derivatives as a function. And how do we define derivatives? It's actually this fella here. It's very similar to what we had just now, right? Just now when we talk about the derivatives at the point, it's actually f of x naught plus h minus f of x naught. But that one is just the derivatives at the point. If you want to make it into a function, if you remember what is function, it's something like a machine. You put in something, then you get something else. You get something, either the same thing or you get something different. And in this case, I want to put in something into this function and I want to get the derivatives. So instead of x naught, we will use x, okay, in the definition of derivatives as a function, of course. Okay, so this is the definition, and also we call this formula here the first principle. Okay, this is also the first principle. Of course, you can do what you did in your high school, like y is this, y equals to this, then y plus delta y equals to something, then you have x plus delta x, that one, then you minus. It's actually the same thing. It's actually the same thing. Okay, because you use equation, remember you use equation 2 minus equation 1, which means as you can see here, this y plus delta y is actually your f of x plus h. Your y here actually is your f of x. They are actually the same. But now we combine everything into one formula, and this is what we call the definition of derivatives. Okay. Another thing that I want you to take note is the notation. Okay, the notation. In case some of you are new to calculus and you never seen this notation, I'm just going to go through this very quickly. Okay, so this f prime x means the derivatives of fx. Okay, we read as f prime x. And we can also, if we want to make it into like a verb, then we dx. This one means differentiate your function f of x. Okay, you differentiate that function. Sometimes people also write like this, dx of y, because you write y equals to something, right? Y equals to mx plus c, for example. This is the same as dy dx. Okay, as you can see, it's actually like a fraction, but not a fraction. Okay, then it means, okay, by the way, the x that we write here means it is with respect to x. You differentiate with respect to x, and this is very important. Like I said just now, at the topics letter, you have different parameters. Sometimes you need to have with respect to time, which is t, or with respect to an angle, theta, something like that. So it is very important that you know who is your parameter. But in most of the case at the beginning, it will just be x. Okay? Then what about if I want to write the derivatives of at the point, derivatives at the point? For this kind of notation, just very simply, you write a line, a stroke, then you will write x equals to x naught. Means the derivatives at x equals to x naught. Just like that. Just like the f prime x naught from just now. Okay, very simple. Then now, what happens if I want to differentiate many times? Like, this is what we call the first derivatives. If you differentiate again, you will write f double prime x. You differentiate again, you write f triple prime x. If you differentiate again, don't give me four hair over there, right? Starting from the fourth derivatives, you write like this. Okay, x and so on and so forth. Then for if you want to write dy dx, okay, first derivatives is just dy dx. Second derivatives, okay, you need to be very careful, yeah, because you are actually squaring this one. So the notation is the 2y dx square, then, oh sorry, I shouldn't write equals. Then becomes like this, then you differentiate again the 3y dx 3 and so on and so forth. Okay, so this is about the notation in case you are new to calculus. Okay, then now we will do some exercises, which is actually using the definition find the derivatives, which means using first principle, which is this formula. Okay, it's actually very simple if the function is not very complex. Okay, so the first one, okay, we'll just write the notation. Remember, f prime x. Okay, and what is the formula? Remember, you have a limit as h approach 0 of f of sorry, I should write f of x. Okay, I use blue color. F of x plus h. So now instead of x, you replace all your x with x plus h. So it will just be 1 plus the square root of x plus h, right? Do not confuse yourself, you better put a bracket. Then minus, you need to minus f of x, right? Minus f of x. Then f of x, you just copy. Again, you better put a bracket in case you confuse yourself. Okay, h. And now, as you can see, if I expand this, okay, I'm just going to expand this here. This will be a minus, right? Minus. Then this 1 and 1 can cancel. Okay, I throw away this bracket. It will just be the square root of x plus h minus square root of x. Am I right? Remember what you learned in limits? Whenever you see two square roots, what you do? Rationalize. Multiply by conjugate. This is why all the technique that you learned in the last chapter is very important when it comes to first principle. And also the concept of limit itself. Okay, so we'll just have limit. Remember this a plus b, a minus b, which is a square minus b squared over, okay, don't forget, yeah, you are multiplying the conjugate for both numerator and denominator. And now this x and x can cancel out each other. This h and h can also cancel out each other. So at the end of the day, okay, actually you can sub in your h already, right? Because you will not get over 0 at the bottom. Okay, just sub in 0. On top, it will just be a 1 over square root of x plus square root of x, which is 1 over 2 times square root of x. And this is it. This is the derivatives of this function. Okay, it's a little bit messy here, but if you know how to evaluate limits and you have very strong concept, you should be able to do this very quickly. Okay, like I said, if the function is not very complex, you usually can do it with first principle, no problem. Okay, but in advanced level, nobody will do this. After you learn the differentiation rules, you will not do this every time unless you need to prove something. Okay, then we gotta move on to the second one, which is also a square root, so you know that you definitely need to do rationalize again. Okay, f prime x equals to the limit as h approach 0, square root of 2. Remember, replace all your x with x plus h. Okay, then minus your f of x, right? Square root of 2x over 5 minus 5x over h. So the first thing I do here is I try to expand this bracket. This will just be minus minus becomes a plus. Am I right? And secondly, I want to expand this bracket. It will be negative 5x minus 5 hash. 5 hash. So that this 5x and 5x can cancel. And I want to take out this, I want to split it into two fractions. Okay, let me write one more step for you in case I also want to expand this one, sorry. 2x plus 2h over 5. I bring this square root over, then over h minus 5h over h. Why? Because I want to cancel out this. And secondly, I want to multiply by conjugate, which is rationalized. Okay, so it will just be, remember, I multiply both top and bottom by the conjugate. So on top it will just be a square minus b square. Am I right? Over, oh, I'm running out a little bit out of space here. Okay, 2x plus 2h over 5 plus square root of 2x over 5. And in fact, you can combine two of them together. You can combine two of them together. This is a minus. This 2x and 2x can cancel. This h and h can cancel. So you just have a 2 over 5 on top. Go move on to the next page, okay? Okay, limit h approach 0. We have a 2 over 5 on top and the conjugate at the bottom. And you know what? For this conjugate, we can actually factor out 1 over square root of 5, right? We can factor out this further here. Okay, 1 over square root of 5. Why I want to do this? Because I want to simplify with the one on top, the constant on top. Okay, square root of 2x plus 5 plus square root of 2x. Am I right? And we have a minus 5. Sorry, just now I missed out the minus 5. Okay, then yeah, we can substitute in our value of h already. But before that, we need to simplify the constant, right? I will just write a side note for you. 2 over 5 divided by 1 over square root of 5. 2 over 5 times square root of 5, which is 2 times 5 power negative 1 power half. Negative 1 plus half is negative half. So it is 2 over square root of 5. Okay. 2 over square root of 5, square root of 2x plus 0, plus square root of 2x minus 5. So at the end of the day, just a lot of algebraic manipulation, right? And yeah, these two are actually 2 times square root of 2x, am I right? Minus 5. And these 2 and 2 can cancel. And if you like to simplify, you can actually multiply this inside. If you don't want, also can. But since I already draw the error, get 10x minus 5. Finish. Okay? Then moving on to the third one. Oh, we have a trigonometry. Okay, but don't worry. When you move on to the next lesson, I made a video to derive all the derivatives of these trigonometric function, exponential, logarithmic, and so on and so forth, those functions. If you're interested, you can go and watch my proof. But if not, you can always just refer to the formula list or table during your exam. Alright? But now, since the question asks us to derive it using the definition, we will just do it. F prime theta equals to, remember, limit h approach 0, f of theta plus h minus away. Just copy sine theta, yeah, sine theta over h. And now what is this? Remember, this is your compound angle, right? So compound angle for sine is sine cos, cos sine. Sine cos, cos sine. Then minus sine theta. You may tell me that, oh, why it becomes more complicated? But don't worry. Whenever you see your sine or cos got limit h approach 0, you know that it's something to do with the special trigonometric limits, right? That I also mentioned in the last topic, that two special trigonometric limits will be very important when it comes to first principle, which is the limit as, I don't use theta, I use x approach 0, of sine x over x is equals to 1, and the limit x approach 0 cos x minus 1 over x is equals to 0. Alright, so now you just need to make it into these two forms and just put in 0 and 1 and you will eventually get your answer. Okay? Okay, I already can see it. I will move this around and factor out the sine theta, so that I will have cos h minus 1 over h. I think you can see it already, right? And I'm going to split this fraction, h approach 0 of cos theta sine h over h. So as you can see, this fella here, if you put in the limit, it's actually equals to 0, right? Means the entire thing is 0. Then what about this one? Sine h over h. It is a 1. 1 times cos theta, just cos theta. Hence, the derivatives of sine theta is cos theta. It's amazing, right? How you differentiate a trigonometric function, you become something else. But actually, if you look at the graph and you know that it represents the slope, it actually makes sense. From positive to negative, that one, if you go and play with that, it actually makes sense, you know. Okay? So this is it for the first part of today's lesson. Alright? Okay, now we move on to the second part of this lesson, which I want to talk about one-sided derivatives. Just like what you learned in the last chapter, we have one-sided limits, right? One-sided limits, two-sided limits, and continuity. And now we'll link all of them together. So before we move on to one-sided limit derivatives, let me recap what is. I will write a recap. What is one-sided limits? Okay. So if you have a limit where your x approach c from the right, remember, your c is here, your x is here, you are approaching from the right, then you take the limit of f of c plus h as h approach 0. Am I right? Then if it is x approach c from the left, means your c is here, your x is here, like this, approach from the left, then you take the limit of f of c minus h as h approach 0. Okay, just a very quick revision for your one-sided limits, because here to here is h and here to here is your h. Okay, then what about one-sided derivatives? Remember just now how we define derivatives is actually from a secant line, the slope of a secant line, then that secant line you shift, eventually becomes your tangent line, right? So if you are taking derivatives from the right, like this one, like this part here, okay, meaning you see your secant line, the one in black, is initially like this. Then now I draw a second secant line. Something like this. And now just now was P and Q, right? My Q is here. So as you can see, it is actually like this. Approach, I'm not sure if I can call this approach from the right, but you get the idea, right? It's actually the slope, the secant line actually becomes the tangent line from the right. Okay, so it rotates like this, which means your Q, okay, if this is your P and this is your Q, your Q approach point Q approach point P from the right. Does it make sense? Yes, huh? So this is one-sided derivatives. So similarly, if it is from the left, okay, this is still your P, this is still your Q, and now I draw my second line like this. Okay, now my q prime is here. It's like this, right? My q approach p from the left. This is what we call one-sided derivatives. Derivatives from the left and from the right. It's actually very similar to the concept of one-sided limits, just that now we are looking at secant line and tangent line. Alright? So now, then you might say, oh, what is the point of doing this? If both of them are the same, then there's no point of doing this, right? The reason why we want to look at one-sided derivatives is because sometimes they are not the same, just like your limit. Sometimes your limit from the left and limits from the right are not the same, therefore the limit does not exist, right? Remember? Similarly, if you look at this example here, it's actually a piecewise defined function, am I right? If you want to write it in terms of like fx, it is x squared when x smaller than 0, x when x greater than 0. This equal sign can belong to any one of them because both of them will give you 0 when x is equal to 0. So now I want to find the derivatives of at x equals to 0 from the left and from the right. So the formula is here. Okay, these two, yeah. From the left we are using this definition, right? Okay, because at the left hand side of 0 we are using y equals to x squared. Limit h approach 0 from the left, f of 0 plus h, can you remember, you see, a plus h minus f of a over h. 0 plus h, the whole thing squared becomes h squared, right? H approach 0 from the left, h squared minus 0 over h. This h and h can cancel, so at the end of the day will just be the limit of h approach 0 from the left of h, which is just 0. By the way, if you want to continue to do the one-sided limits, you will eventually get 0, so I'm actually skipping some steps here. Then what about the derivatives from the right? From the right hand side, or on the right hand side of 0, we are using this definition. Alright, so the limit h approach 0 from the right of f plus 0 plus h minus f of 0 over h. It is always minus, yeah? This time is always minus. Why? Because from the definition of derivatives, it is f of x plus h minus f of x, right? So in this case, if you are taking one-sided, it is f of a plus h minus f of a, or f of b plus h minus f of b. It's always minus. Okay, it's always minus. The one-sided here is actually depending your h from the left or from the right. So it is very simple. It is just the limit h approach 0 from the right of h minus 0 over h, which is equals to 1. As you can see, the derivatives from the left and from the right are not the same. One is 0, one is right. Hence, we write a conclusion here. The derivatives does not exist at this point P, 0, 0. Okay, so this is what we call one-sided derivatives. And this is just one type of derivatives that fail to exist. We have many of them. Okay, let me move on to this slide, alright? So just now our case was the first one, right, which is a corner where the one-sided limits, the one-sided derivatives differ. Okay, from the left and from the right are not the same. Then the second condition that the derivatives fail to exist is when you have a cusp. Cusp means what? Means your slope from the left and from the right, one is towards positive infinity, one is towards negative infinity. Like in this diagram here, the slope from the right, okay, the straight line is like this, right? So the slope on the right will approach positive infinity, am I right? Then from the left, the straight line is like this. So eventually the slope becomes negative infinity. And this is what we call a cusp. Okay? Then the third condition is where you have a vertical tangent line, which is obviously, you know that if you have a vertical line, then you will not have your equation of it will just be x equals to something, and you know that the slope will be undefined, right? And when we talk about derivatives, it means the slope of tangent line. The slope of tangent line is now undefined, hence the derivatives fail to exist. Okay, so this is the third condition. The fourth condition is when you have a discontinuity, like if the graph the jump or there's a hole there, then as long as it is discontinuous at that point, means there is no derivatives. Alright, and we actually have a theorem for this later. We'll come to that later. Last but not least, if we have a wild oscillation, then the derivatives also fail to exist. Just like your limits, remember? When we talk about limits that fail to exist, if it is like wild oscillation, it will fluctuate, the value will fluctuate between 1 and -1, remember? Then you say that the limits does not exist. Alright? So that's the concept part. Now we move on to the exercise. So for this exercise, we need to determine the domain points of the function that appear to be differentiable, means have derivatives, continuous but not differentiable, neither continuous nor differentiable. So it's a very simple exercise where you just have to determine the domain of it. Okay? So if you look at this first function, the domain is from -3 to 2 inclusive. It is continuous throughout the graph, right? And it is continuous. There is no like crazy tangent line that have like positive, negative slope. Positive infinity, negative infinity slope. There is no vertical tangent line. There is no discontinuity. There is no oscillation. Hence, it is differentiable throughout the domain. So for A, it is just, for A, it is just from -3 to 2. Okay, then none for this, none for that. All of them are continuous and differentiable. Okay, very simple. The next one, okay, as you can see, we have a discontinuity, right? We have a discontinuity at x equals to 0. And we know that as long as it is not continuous, it is not differentiable. So I answer question C first. We know that it is discontinuous at x equals to c. What is the reason? Okay, the reason is the limit from the left is not the same as the limit from the right, means the limit does not exist, and some more it is different from f of 0. F of x at 0 means discontinuity lah. Discontinuity. As long as it is discontinuous, automatically not differentiable. Okay. Then for part A, for part B, is there any curves, any vertical tangent line, any oscillation? No, right? So it is differentiable from -3 to 0, not include 0, and from 0 to +3, not include 0. There is none, and there is no points that is continuous but not differentiable. Alright? Then move on to the third one. Okay, so this is which one? Which case? Case number 2, right? It's a cusp, because you see the tangent line from the left, it is like this, like this. I mean approach 0 like this, like this. So eventually it will become a vertical tangent line. And if it is going down like this, means it is a negative slope, negative infinity. What about from the right? It is like this, like this, like this, like this, eventually also becomes a vertical tangent line. It's going up like this, so means eventually it will becomes positive infinity. From the left, the slope is negative infinity. From the right is positive infinity. We call them a cusp, and it is discontinuous. Not discontinuous. It is not differentiable. Hence, let me answer number B first. It is continuous. It is continuous at x equals to 0, but not differentiable. The reason, what is the reason? The limit from the left is the same as limit from the right, means the limit exists, and some more it is equals to f of 0. But it is not differentiable because the one-sided derivatives differs. Okay, once the derivatives from the left is negative infinity, the derivatives from the right is positive infinity. Okay. With that, automatically you can answer your part A, which is from -1 to 0 not inclusive, and 0 to 2 not include 0. Then it is continuous throughout, hence there is no point that is continuous, but neither continuous nor differentiable. Okay, so this is all for the exercises for today's lesson. And now I want to connect limits, continuity, and differentiability using this theorem. But before we look at this theorem, let me do a little bit of revision. Okay, revision on limits and continuity. Like I said, today's lesson will be mainly on concept. We will not do this. We will not do all of this later part of the chapter. Okay, so in limits and continuity, I told you that there are 4 things that we have to take note, which is number 1, f of x at c, limit from the left, limit from the right, and whether they are the same, limits from both sides. Okay, so in order for a limit to exist, what is the condition? Exists. The limit from the left and from the right must exist, and they must be the same, right? The limit from the left and the limit from the right, they must be unique and they must be the same. Then what about continuous? Continuous. We have one more condition, right? The limit from the left is equals to the limit from the right, which means the limit exists. Limit exists. And one more condition, it has to be equals to f of x at c. Okay? Then now, what about differentiability? Differentiable. I'm not sure about the spelling. Okay, so for a function to be differentiable at a point, of course the limit must exist and it has to be continuous. But let me move on to let's look at the theorem. Okay, if f has the derivatives at x equals to c, then f is continuous at x equals to c, which means if we say that it is differentiable at point c, means automatically we can say that it is continuous at point c and the limit also exists at point c. Okay, so now I'm going to prove this theorem. Okay, proof. What is the theorem? The theorem said that it has the derivatives at x equals to c, then it is continuous. So what do we need to show? We need to show that we need to show that the f prime, what's that? We need to show the limit as at x approach c of this one. If we show this, that means it is continuous, right? And what is our prior condition? See, our prior condition is that f is differentiable at that point. So we will just write, given that f prime c exists. How do we relate this f prime c and these two fellows together? You need to make it like, you need to make this somehow into the definition form, and you show that if this is differentiable at that point, hence it is also continuous at that point. Okay, so now I'm going to, instead of taking x approach c, I'm going to take h approach 0 of f of c plus h equals to f of c. Okay, it actually means the same thing, right? X approach c means the difference between x and c is very small. Means if there is a h exists in between x and c, h has to approach 0. And the reason why I want to write in this form is because later when I want to switch into something like the definition of derivatives is easier, right? It's easier because you know that just now you have a f of x naught plus h minus f of x naught, this kind of thing. So it will be easier for me later. Okay? So this is the setup and the direction. Now, like I said, I will start with this fellow here. I will start with f of c plus h. How do we write this f of c plus h in terms of like the definition of derivatives? So if you have a graph like this, your c is here, your c plus h is here, your f of c is here, your f of c plus h is here. Okay, like this. Okay. What is your f of c plus h? It's actually your f of c plus something else, right? F of c plus something else. Okay, so it is f of c plus something else. And what is this something else? We don't know. But it is actually, if you don't know, then we just write c plus h minus f of c. Actually, it's cheat a little bit lah. You know that the difference in this and that is this minus this, which is actually what we want, right? Remember, this is very close to our definition of derivatives already. I just need to something over h, right? I just need this over h. I just need this to be over h. But whenever you do to one term, actually you have to do it for everything here. You need to do it for the other side as well. Okay, and this one, okay, maybe I should write like this. Like this. Okay, and now I will just this one bring over. It's a little bit messy here, I know, but forgive me because this is actually very hardcore, very technical. F of I want to leave it in this form. So I will leave my h this side. Let me erase this part to give me some space. I will just leave my h outside. Now I'm going to take the limit as h approach 0 on both sides. Limit h approach 0, c plus h equals to limit h approach 0 of f of c minus, plus, let me erase this part here. Okay. In fact, you know what? I'm just going to leave it. Then I write another limit. F of c plus h plus f of c over h times the limit h approach 0 of h. Now what? Now this fella here is our f prime at c, right? Am I right? It is our f prime at c. Which means, and we also said that f prime of c exists. Means it is not anything crazy like undefined, indeterminate, or anything crazy. And we know that if we substitute in 0 for this term here, 0 times anything is just 0 times anything normal is 0. Hence the whole thing here will just be 0. Am I right? So at the end of the day, you will have the limit as h approach 0 of f of c plus h is equals to, there is no h for you to substitute in, just write f of c. And what is this? This and the other same. If this is true, means this is also true. Means what? Means it is continuous. Which means if we set the condition that f of x exists at x equals to c, automatically it is continuous because we can prove this. Because we can prove that the limit as x approach c at that point is equals to f of c. Finish. And this is the end of proof for that theorem. But this is something that you need to be very careful. The converse of this theorem is not true. Like if it is continuous, it doesn't mean that it is. If it is continuous, it doesn't mean that it is differentiable. If it is continuous, it doesn't mean that it is differentiable. Okay, if it is continuous, it doesn't mean that it is differentiable. Just now we had an example like this, right? Just now this one. Yeah, this one. You said it. You see, it is actually continuous at x equals to c. The limit from the left and from the right, and f of 0 is the same, but it is not differentiable. Another example was this one. No, this is not continuous. Yeah, this one. Also continuous at x equals to 0, but not differentiable. So the converse of this theorem is not true. Alright? So this is the relationship between limits, continuity, and differentiability. And we have covered the concept of differentiation from the tangent line problem. First principle, the relationship between limits, continuity, and differentiability. And the next lesson will be discussing the differentiation rules, which shall make your life so much easier that you don't have to go through first principle again and again. Alright, so that's all for today. See you guys in the next class.